Now we are going to understand Lenz's law. We have already learned the Faraday's law of electromagnetic induction, which states that the magnitude of induced EMF in a circuit is equal to the time rate of change of magnetic flux through the circuit. So we began the chapter by discussing a few experiments which were done by Faraday and Henry, from which we were able to see that a change in flux induced current in a coil which is placed in the magnetic field. By changing the flux associated with a coil, we can induce a current in that coil. And the reason for the current is the induced EMF. Now in the expression of Faraday's electromagnetic induction, we saw that there is a negative sign, that is E is equal to the induced EMF E is equal to minus d phi by dt. And the direction is specifically given by Lenz's law. A German physicist Heinrich Friedrich Lenz deduced a rule which gives the polarity of induced EMF, and this rule is named as Lenz's law. And according to Lenz's law, polarity of induced EMF is such that it tends to produce a current which opposes the change in the magnetic flux that produced it. That is, we have understood that a change in magnetic flux causes induced EMF through a coil. So the reason for induced EMF is a change in the magnetic flux. And according to Lenz's law, the polarity of that induced EMF is such that the current which is produced in the coil will be having a direction that opposes the change in the magnetic flux. And that is the reason for the negative sign in the expression of induced EMF. The EMF induced produces a current that opposes the change in the magnetic flux. Now let us analyze this law by applying it. Suppose we are having a coil and we are bringing the north pole of a bar magnet towards our coil. And here we can understand that as this north pole of the magnet is moving closer to the coil, the magnetic flux associated with this coil is increasing. That is, the strength of the magnetic field is increasing, which increases the magnetic flux. So the change in magnetic flux here is an increase in the magnetic flux. So the change that occurs in the magnetic flux here is the increase in magnetic flux. According to Faraday's law, since the magnetic flux associated with this coil is changing, an induced EMF will be produced. And the direction of that induced EMF is given by Lenz's law. And Lenz's law states that the induced EMF produces a current that opposes the change in the magnetic flux. So a current in this coil will be produced such that it opposes the change in magnetic flux. Here the change in magnetic flux is that the magnetic flux is increasing. So current should be in such a way that it reduces the magnetic flux. So the current produced in the coil should reduce the change, that is, should decrease the flux. Now the current should be produced in such a way that this face of the coil should become north pole so that it can repel the north pole of the magnet that is coming closer. And we know that a current in anti-clockwise direction will make this face of the coil to act as a north pole. North pole means the magnetic field produced should be coming from that face, and we know that using right hand thumb rule we can find here if the direction of current is anti-clockwise, that is the four fingers are placed anti-clockwise, then the thumb direction is the direction of field that is coming out from this face of the coil. Therefore, the flow of current in anti-clockwise direction makes this face of coil to act as a north pole and thus repels north pole of magnet and hence reducing the flux associated with this coil. So what we have analyzed here is when we are bringing a north pole of the magnet closer to our coil, the magnetic flux associated with the coil is increasing, because as the north pole of the magnet comes closer to the coil, the strength of the magnetic field increases, and that brings an increase in the magnetic flux associated with the coil, and therefore the current induced in the coil tends to reduce that change in flux. That is, since the magnetic flux is increasing, the current in the coil tends to reduce that magnetic flux, and in order to reduce the flux, the current flows in anti-clockwise direction, which makes this face of the coil to act as a north pole and thus repel the magnet and reduces the magnetic flux. Now in a similar way, if we imagine that the north pole of the magnet is taken away from the coil, that is, if we are moving away the north pole of the magnet from the coil, the flux associated with this coil is reducing. So here the change in magnetic flux is that the magnetic flux reduces. So according to Lenz's law, the current induced in this coil will be in such a way that it should increase the magnetic flux. The change in the magnetic flux that is occurring here is a decrease in the magnetic flux. So the current induced in it should be opposing the change, that is, it should increase the magnetic flux. So here this face of the coil should act as a south pole so that it attracts the north pole of the magnet and thus increase the magnetic flux. So for that the current should flow in clockwise direction. Thus the direction of current in the coil becomes clockwise so that it attracts the north pole of the magnet, which is taken away from the coil, and thus opposes the change happening to the flux associated with this coil. So this is how Lenz's law is applied, and according to that the induced EMF will produce a current in a coil such that it opposes the change in the magnetic flux that produces that induced EMF. So we have understood how Lenz's law gives the direction of induced current, and we have analyzed an illustration of the Lenz's law also. Now the correctness of Lenz's law can be analyzed with the help of law of conservation of energy. Lenz's law holds the conservation of energy. Suppose in the illustration that we have already seen, that is when a north pole of a magnet is brought closer to a coil, then according to Lenz's law, this face of the coil acts like a north pole such that it repels the bar magnet and thus reduces the magnetic flux. Now instead of north pole, what if this was south pole? If Lenz's law is not correct, then instead of north pole this should be south pole, right? So if this was acting as a south pole, that is if the current was flowing in clockwise direction, we are checking the correctness of Lenz's law by analyzing the contradictory. So if the current in the coil was such that this face acted as a south pole, then definitely the north pole of the magnet will be further attracted to the coil. That is, it will keep on increasing the magnetic flux. So in this case we can say that with a little push on this magnet that we give to initiate this process, the velocity and the kinetic energy here will continuously increase without expending any other energy, which is actually a violation to the conservation of energy. We know that energy can neither be created nor be destroyed. It is only transformed from one form to the other. So with a little energy given to this magnet, an excess amount of continuous energy is obtained, which is not possible. So definitely this face of the coil should act like a north pole when a north pole of the magnet is brought closer to this coil so that the law of conservation of energy is not violated. So the contradictory is wrong, hence correctness of Lenz's law is convinced. Thus, we have understood the correctness of Lenz's law with the help of conservation law of energy.